Ewald Hering was born in Utzkerdorf, Germany in 1834. At the age of 19, he studied medicine at the University of Leipzig under Weber, Fechner, Funk, and the zoologist Carus. He became a physician and was known best for his studies regarding color vision and spatial perception. Around 1850, a German physician by the name of Hermann von Helmholtz and Thomas Young, seen here measuring the size of his eye, developed a trichromatic theory of color vision. This theory states that when perceiving color, the human eye actually sees a combination of three primary colors: red, green, and blue. This is because the eye has three types of cone photoreceptors that perceive different colors at different wavelengths. Long wavelengths are perceived by the brain as the color red, whereas medium wavelengths are perceived as green and short wavelengths as the color blue. By combining varying proportions of these three wavelengths, any hue can be created. Hering, however, disagreed with this and observed that there were certain things the trichromatic theory of color vision could not explain. From this, he developed the opponent process theory, stating that the photoreceptors in a human eye are actually linked together to form three opposing color pairs: yellow-blue, red-green, and white-black. The activation of one member in the pair inhibits activity in the other member. So if you see yellow, the activity of blue will be prevented. Same for red and green and white and black. This applies vice versa to the pairs. Simply put, you will never see a bluish yellow or a reddish green. To understand this better, let's take a look at complementary after images. Try this experiment. Did you see how the color switched in the after image? Try it again if you couldn't. What you should notice is that the original colors are reversed. Red is now green and vice versa. The same happens with blue and yellow. According to Hering's opponent process theory, the cones and rods that perceive color gets worn out and tired by the extended inspection, which reduces the inhibition in the pairing system. This allows the relative activity level of the inhibited pair to increase and result in its color being perceived afterwards. In the 1890s, using his knowledge on color vision, Hering created a color blindness apparatus with Rolf in Prague. The subject will look down the main tube and see a circular field that was half red and half green. By moving the reflecting screens, the subject could change the hue of one half, the brightness of the other, and the saturation of both together. The subjects were asked to make the two halves match. If this could be accomplished, then the subject was deemed to be colorblind. If given two different lights, red and green, no matter how much the intensity or photons produced changes, a person with normal color vision will always absorb different amounts of photons from both sides. They will always see red and green. However, for colorblind people, because the sensitivity of their receptors are different, in this case sensitive to red only, the adjustments made to the intensity of the light can result in the same number of photons being absorbed, meaning by adjusting the intensity of green, it could look the same as red. Over the years, improvements in technology and new discoveries have allowed us to realize that there are various types of color blindness. Color blindness is classified according to the affected cone types and the degree of the deficiency. There are three cone types that absorb the varying wavelengths mentioned in the Young-Helmholtz trichromatic theory of color vision. The cone types differentiate by which wavelength they take in: long, medium, and short. These three cone pigments allow people to see different colors. However, not everyone has all three cones. People whose vision is based on all three cones is called trichromacy, 2 cones dichromacy, and 1 cone monochromacy. Let's look at trichromacy first. People with normal color vision have all three cones. They would be able to perceive the number 29 as distinct from the rest of the dots. They would also be able to see the bee on the pink flower. Those who have dichromacy are missing a cone, which means depending on which cone they are missing, they would not be able to perceive a certain color. People who are missing the L cone have a red-green deficiency. The generic defect name is called protanopia. The number 29 is hard for them to see, and the flower is perceived as blue rather than pink. If the M cone is absent, the person also has a red-green deficiency. The generic defect name is called duotanopia. The number 29 is also hard to see, and the flower is now perceived as a grayish-blue. If the S cone is absent, the person has a blue-yellow deficiency. The generic defect name is called tritanopia, and this is a rare situation for people to have. Here, the number 29 has turned orange, and the yellow and the surrounding dots are now gone. The pink rose is also now red. To have one cone is very rare, and it is called monochromacy. Everything is perceived in shades of gray. At the end of it all, Ewald Hering's opponent process theory has allowed people to realize that the color vision process occurs not only at the receptor level, but at a subsequent neural level as well. His color-blind apparatus revealed the necessity of introspection in science, because only the subjects could say whether or not the two wavelengths appeared the same. It is due to Hering's discoveries in color vision that many more discoveries and investigations would be made. His contribution to psychology and physiology is one that would be noted forever.